Hello, everybody, to the GRoW final conference, and thanks you very much for the opportunity to present our project and the name of our project team. In the following, I will give a brief overview of the GoCam project, with a focus on the implementation of strategic development goals in coastal aquifer management. The archivement of water supply security is one outstanding aim of the Sustainable Development Goals of the UN Sustainable Agenda of 2030, affected by climate change, saltwater intrusion, and human impacts such as intensive agriculture, freshwater supply, especially in coastal regions, is nowadays still threatened in many countries worldwide. For case studies, areas have been selected for which it will be essential in the future to discuss the water resource management to archive future water security. In Germany, the case study areas are Saint-de-la-Meuns and Großenkneten in northwest Germany at the North Sea coast. Internationally, case study areas are GRoW, Bissau at the eastern coast of Brazil, Antalya in South Turkey, and Buffalo City in South Africa. Now we'll come to the project goals. Current global development involvement, water demand growth, as well as threats imposed on freshwater resources linked to global climatic changes, increase the stresses include on water systems and could nowadays still increase conflicts among stakeholders. Therefore, some of the keys for the successful implementation of IWRM among different stakeholders are, firstly, the more accurate assessment of the state of water resources of coastal regions using highly complex hydrogeological modeling tools, modern subsurfaces reconstruction techniques, as well as complex monitoring systems. Secondly, the development of the base for an improved forecast of the availability of water for future economic and ecological purposes by discussing and applying various management scenarios, climate change scenarios, and bias correction methods. The third and most challenging aspect is the harmonization of conflicting stakeholder position within a water basin to archive compromises for an overall improved and sustainable water management practice and to gain transparency and objective in decision-making process. All three positions were addressed within the project of GoCam, with an emphasis on the third and probably most difficult part, the dialogue among stakeholders in the water sector. To address the difficulty, the online CAM, Coastal Aquifer Management Dialogue Platform, in short CAM tool, was developed as a new management instrument for IWRM challenges that directly tackles the aforementioned key conditions for a successful IWRM. The CAM Dialogue platform is a free, web-based geoinformatics system that uses Open Geospatial Consortium (GOGC) standards and is built on the GeoNode technology. The CAM platform is praxis-orientated as it was developed in direct cooperation with water agencies, water supply companies, and local universities. The tool provides an online environment that allows groups of stakeholders to share and visualize and bundle all relevant data on a particular IWRM case, while each user keeps full administrative control over his data. Thereby, the barriers for sharing interaction between stakeholders are decreased. CAM not only provides a bundle of and easy-to-grasp representation of the current state of water management, but it also allows the visualization and especially the evaluation of future changes. Therefore, the tool provides newly developed physically based water indicators, individual definable target functions, and MCDA components for a user-oriented evaluation to increase the transparency and objectivity in the IWRM process and the mutual recognition of the diversity of the different stakeholder positions. Further, the CAM tool is user-friendly and easy to access. And now I want to give an application example. Assume a water supply company wants to obtain groundwater extraction.
Mr. Hilbig, sorry to interrupt you. I just got the information that there are two different presentations. So please switch your screen, I guess. Is that the correct thing to do? So please switch your screen so we can see your presentation.
No. It's better.
So this is the newest presentation from your side. Thank you. Go on. We managed to do it. Thank you.
Okay. Okay, we'll start again. Assume a water supply company wants to obtain groundwater abstraction rights in a given area from the local municipality. Possible stakeholders might be the Environmental Protection Department and Agriculture and Irrigation Department and supplying company. In step 1, you can see it here in the picture, the company is required to append an environmental impact study to the application for the municipality to be able to evaluate whether the intended groundwater abstraction would not violate environmental protection laws, threaten irrigation practice. The respective environmental impact study includes an hydrogeological model for assessing the impact of the 3 different pumping scenarios on the groundwater levels and the base floor and concerned catchment. The main model output that serves as indicator for the municipality to evaluate the company's application is the base flow change under the 3 pumping scenarios A, B, and C. In step 2, here, in our example, the company wants to obtain groundwater abstraction rights, uploaded the model results on the ChemDialog platform and added them to a self-created IWRM project. They have to do it as a registered user. In step 3, for uploading the data, the model layers are converted with the standalone software ChemUp into a data format that is compatible with the Chem tool. In step 4, ChemUp communicates via a cloud server with the online Chem tool server to automatically add respective layers to the user's account in the Chem tool. In step 5, once the registered user uploaded the model results and additionally relevant data and added them to his IWRM project, the data can be viewed in the GIS interface of the ChemDialog platform by other registered users that were invited to join the respective IWRM project. In the example, the 2 departments of the example municipality, environmental protection and agriculture and irrigation, have access to the data via the Chem tool as registered user. In step 6, on the top of the picture, the representative data is centrally and automatically being organized on the Chem tool server in the GDatabase. In step 7, depending on the access permission granted by each user, the content of created IWM projects on the ChemDialog platform can also be viewed by unregistered external users. And finally, in step 8, the functionality target function will be explained by using the indicator base flow change on a subcatchment level. Both stakeholders can evaluate the model base flow changes in the subcatchment level as inducted the pumping scenarios A, B, C, applying the target function functionality. In an interactive window, the picture on the side, each user is asked to select the desired scenario and the associated indicator of interest. In the next window, the user will be able to define thresholds for the values of the selected indicator that automatically define target functions. And the target function will interpolate linearly between each set threshold value. Hence, the target function translates the numeric values of the indicator layer into a layer with an index of target fulfillment in accord with their personal water management target. A preview of the calculation is available, which is carried out on the fly on this way. In our example, both mentioned municipality departments set their first threshold at 0% base flow change, which translates into a water management target fulfillment of 100%. However, the irrigation department set their second threshold at 30% base flow degrees, apart from which the target fulfillment would be 0%, because they would be unable to met their water requirements in dry periods. On the contrary, the Environmental Protection Department set their limit at the 10% base floor, from which on their target fulfillment would be 0%, because otherwise the ecologic water requirement would not be met in dry periods. At the end of this process, all three stakeholders in our example can compare online different degrees of target fulfillment for each stakeholders under the three pumping scenarios via pipe tool in a GIS view here on the right side. In this process, the stakeholders are enabled to share the problem perception and visually compare the diversity of different stakeholder positions. At this point, the group of stakeholders could meet and discuss personally to agree on the most suitable pumping scenarios or assess whether other scenarios would need to be modeled and added to the CAM tool for eventually archiving a higher mutual consent in the IWM challenge. The base flow given in the example is one indicator which could be subject to combined evaluation and which is derived from the results of the hydrogeological modeling. To address the UN SDG targets 6.2, 6.4 and 6.6, further evaluation parameters and related physical-based indicators are developed in the GoCam project. The indicators used in CAM are water management variables and appraisal factors for the hydro systems and their physical and socio-ecological settings. In the course of a participation process, 8 indicators were identified and implemented in CAM. The weighting of the indicators as well as the objective function for the evaluation can be selected, adapted and discussed by different users, for instance, from water supply companies and the agriculture sector. At the end of the presentation, I want to summarize the most important aspect. Our aim was to inform policy about the development of coastal aquifer systems, which was successfully archived by the development of CAM. CAM tool provides a bundle and easy to grasp representation of the current state of water management and allows a visualization and evaluation of future changes. Due to open data structure of CAM, it can be supplemented by further indicators and maps, and is transferable to other regions. The CAM platform is online and open for access for different users like water agencies, water supply companies, and universities worldwide. This makes a CAM a valuable tool to transfer the scientific understanding of water resources and the modern practice-oriented water management and governance structure. The tool archives a state of development that allows interested users to apply the tool in their personal context, including all of the desired functionalities. However, as the tool was developed in the framework of a joint research project called GoCam, the tool and its functionality underlie a constant development process. Currently, several case studies are being carried out internationally for evaluating the abilities of the CAM tool and for enhancing the user experience with the tool. Interested readers are invited to start their own project on the CAM Dialog platform and are more than welcome to contribute to the ongoing refinement of his work's flow and functionality. At the end of the presentation, I would like to draw your attention to the online presentation of the GoCam Dialog platform, our project publication and posters, which can be viewed on our GRoW marketplace. And finally, we would be also happy if you take part in our webinar tomorrow at 10 o'clock a.m. Thank you for your interest.